let's look at this. We've taken the same experiment and done it with 30 students instead of 9. The data's been run. Regression line has been given. Here it is. Look at that. They gave us the standard error of the slope. And what is the slope of the line? Negative 1.517. All right, that's that one sample slope came out to negative 1.517. So far, so good. Now, if I were to take another sample of 30 students and do the same thing, would I end up with the same slope?
Probably not.
Not likely, right? Why? Yeah, variability exists, if we didn't know that, right? Sampling variability. Will create new results or different results. We're not surprised. That's why we have to do multiple trials, right? To see what is the pattern of this. Now, we're going to construct a 95% confidence interval for the slope of the real population line. There's no way we're going to collect all that data and find it, but we're going to try to estimate it with a confidence interval. So the parameter that we are trying to estimate is big B, beta. It's the true population slope for rho being X and score being Y. In that drawer over there. The true population slope for rho and score.
I'm going to pick up my food from the NHS thing that I brought. So here's my time.
What is the statistic going to be?
Little English B.
Little English B. Do we know that? Yeah, negative 1.517. They just gave us that, right? That's what we do know. We're going to use that to build a confidence interval. Now, remember confidence intervals? Yeah, that whole we are 95% confidence business. Now, so in the state step, if we were doing our state plan do conclude, in the state step, this is what we would write. We're trying to estimate the true population slope for the LSRL where X is rho and Y is score at 95% confidence, okay? Now the plan step, the conditions are different than what we're used to, okay? We're used to just random 10% normal, right? There's a lot more conditions when we do slope. But there's good news and bad news, okay? Bad news is there's 5 of them. It does make an acronym of LINER, or liner, however you want to say it. Liner. The good news is 95% of the time they're going to make a statement in the question that says, assume all conditions are met, so you don't ever have to do them. Very rarely will you have to do them, okay? Promise, promise. It's too much time consuming. It's not worth it. So here's what the conditions are going after, though. Linear. What has to be linear? The scatter plot needs to show a linear relationship. Also, the residual plot cannot have any curved pattern to it. So, fairly linear, no curvature here. So check, check, right? So provided, all we have to do is eyeball it and check those things. The second thing is independent. What am I doing with independence? It's not the 10% condition thing. It's that each observation is independent. Each student's score is independent of each other, okay? So each observation is independent of the next, all right? Now we come up to normal. This is where we're going to do normal distribution, but notice what we're looking to be normal. We're looking at a dot plot of the residuals. So that's going to be provided. They calculated all the residuals for us, threw it on a dot plot, and we are, like before, if we had to create our own dot plot, we'd have to look for strong skewness or outliers, right? It's the same thing. Do we see strong skewness or outliers on this? Nope. So we're good. All right. Equal SD. All right. this is talking about standard deviation of the residuals. So the easiest way to check on this is to look at your residual plot and look for any kind of Christmas tree shape, like the triangle, the sideways triangle. If you see that, then it fails this condition. Do you see that here? No Christmas trees, we're good. Okay, equal standard deviation of the residuals. Kind of we're looking at that scatter. And then lastly, it's that whole random assignment. Are the treatments randomly assigned? Yes. So I would put in here random assignment. Okay? So that's the conditions. You will get more practice with that as we go along. But you can see that took 3 different outputs, right? 3 different graphs to look at. So that's kind of why you're going to see your packets are thicker, because you're going to be given all that stuff. And you're going to be given all these output tables with all your values. You just have to find what you need out of it, okay? So to construct the interval, when we do this, we are going to start with our slope, plus or minus. Remember, confidence intervals have plus or minus. And we use a critical value. And so when we do slope, we use T star. And then we would do the standard error of the slope. Now, one little special case, standard error of the slope is given to us in the output, isn't it? In this case, it was given to us way at the beginning of the page. They gave it to us. Now, do you remember with T star we have to do degrees of freedom? What did we do for degrees of freedom before? Categories -1 or n -1, right? So when we're dealing with regression equations, in this case, regression equations, we have to estimate slope and y-intercept, right? There's 2 things that we're estimating, so we have to subtract 2 instead of 1. But this is the only case you do it for slope, okay? So when you do degrees of freedom for slope, you have to do n -2. All right, so let's construct this interval. Do we know the sample slope? Yeah, they gave that to us. -1.517 plus or minus. I'm going to leave a space for T star. And standard error, they gave that to us as well, 1.33. Now, little mini review. How do we find T star?
Isn't it just, you did a TCDF
Huh?
of the confidence interval, so you had a 95%, it's TCDF.
You can? Yep. I think when we did chapter 8, we did it like this, where we looked at 95 in the middle, and the tail would be 0.025, right? And we go to inverse T and put in the tail measure. Does that ring a bell? It's been a minute, hadn't it? And then degrees of freedom. If I have to subtract 2, how many students did we have in the sample? 30. 30 minus 2 is 28. So I get 2.048 is my T star. Okay. And then you would just crank it out, and when I do all that, I get -4.7, or no, 24, sorry, not 7. 4.24 to positive 1.33. I'm sorry, 1.21. I read the wrong one. So sorry. All right. Now's your favorite part. How do we conclude an interval? Yep, here we go. We are 95% confident that the interval from -4.24 to 1.21 captures what? The true What are we trying to estimate here?
Slope.
Good.
Beta slope.
Slop. I totally wrote spelled that wrong. Slope of the population LSRL where X is row and Y is score. Okay. So a little bit of new verbiage, but not bad. Not too bad. Now, if we think about it, do you think there's convincing evidence from this interval that there is a relationship between?
No. 0 is part of our interval.
0 is part of the interval, so 0 could be a possibility, right? So it may not be any relationship. Everybody tracking with that logic? Remember that? 0's in there, so there may not be a relationship. You see it? If it was all positive, then we would know there's a positive relationship. Or all negative, we would know it's all negative. But since it's negative and positive, there may not be any relationship. Does that surprise you? No. It doesn't surprise me. All right. We're going to just do the top of this page, and then we'll start tomorrow with the practice confidence interval just to kind of warm us up. And then we'll do the same thing but with a hypothesis test. And that's all of 12.1. It's really not bad at all. Okay? So when I do my state plan do conclude, when you do state, you're going to say beta is the true slope of the regression, or LSRL, for what do you suppose?
Explanatory response.
Yeah, X in context and Y in context. And then you can name the confidence level that you're trying to achieve here. Plan step, remember we have to name the procedure. So be careful, you have to name it as the one sample t interval for slope. If you don't say for slope, do you see how it can be misinterpreted as for means? Yeah, you gotta be careful. For slope. Conditions does make that acronym of liner. But otherwise, we're hoping and praying that it just says conditions are met, right? Yeah. Most of the questions I've seen on the AP test, if they even ask this question, it's provided. So it's said. Well, I can't say I've looked at every AP test, but the ones I have looked at, it says the conditions have been met. Okay. Then lastly, the do and conclude. What did our interval look like? Well, let's just put our symbols in here. We did B plus or minus T star times SE of the slope. And remember with T star, my degrees of freedom was going to be n minus 2. And how will I know the SE of B? That will be given to you in an output somehow. Okay, it'll be given to you. So it's just a matter of putting the right values in your equation and going with it. All right? So we'll stop there for today and pick up where we left off tomorrow and finish that last simulation. Okay, so a thrill seeker wanted to try to travel across a large field while being suspended in the air by holding on to balloons. Maybe they just watched the movie Up and thought they could do it too. I don't know. In order to determine the number of balloons needed per pound of weight, he did a preliminary study. He selects a random sample of 20 rocks of various sizes. He weighed each one and also determined how many balloons are needed to lift the rock. Here's the output of the regression analysis of the data, which is actually right here. And we'll bring it down where you can actually read it. Yeah, we need that to be able to do what we need to do. Okay. So there it is. It says construct and interpret a 90% confidence interval for the slope of the regression line. All right, so we're going to go through the 4-step process, see what we can do here. So in our state step, we need to explain what it is we are trying to estimate. And remember, its slope gets the symbol beta. So we call it the true population slope of the LSRL where, and then we put in our context, where x is equal to, what are we talking, the weight in pounds, and y is equal to number of balloons. Okie doke. That's all we need in a state step when we do intervals. All right, plan step. Remember the name of the test here?
Minor. And T-start interval.
It's a T interval. It's a one sample T interval. For slope, remember? We have to add that little thing. Because a T interval could be for means, right? But this is for slope specifically, so this is where we have to specify. Now we have to do the fabulous 5 conditions of the liner. I promise you're not going to have to do this many times, but I want to model how to do it, so when you have to, if you have to, you're not like, she never did it. Yes, I did. Okay? L stands for what? Do you remember? Linear. How am I going to know if it's linear? Look at the scatter plot. Does it appear linear? And then we look at the residual plot to confirm. Does it confirm the linear with no pattern? Yeah. So I use my words and explain that. I would say scatter plot appears linear. Residual plot shows no pattern. So we're satisfied. I stands for what? Independent. How many rocks are we using? 20. Is 20 less than 10% of all rocks? And are all rocks independent of each other? I think so, right? Right? They don't affect one another. They're just rocks.
Why does only like a limited amount of rock?
But then you could break it and then you doubled it, right? So it's exponentially possible. N, what does N stand for? What is normal? What is it I'm looking for? In what, though? The dot plot of the residuals. That's this thing right here, right there.
Oh, it looks just, guys, just gotta look like normal. Oh.
Right here, this thing. Do we see anything unusual, weirdness? No, And if you ever had to do this, you won't find any crazy stuff that's going to disqualify it. So you would say dot plot of residuals shows no skewness / outliers. You have to communicate to the reader what it is you'd be looking for and where you would be looking, okay? All right, E stands for, this is the weird one, equal standard deviation of our, basically of the residuals. Do you remember where do we look for that?
You look at the residual, like the residual block, right?
Yep. Look at our residual plot, and we're looking to see that basically that the residuals, that's that distance from that midline, right? That it's pretty varied. It's not making a pattern like the tree pattern. Like it doesn't start with very low residuals and get really high, or vice versa. It's pretty scattered, right? So it's equal, similar variability for all the x values is what we're going for, okay? So we would say on the residual plot, shows similar variability for each x. Sorry, I'll scooch that up for you. And R, what is R?
Random.
Random. Was our sample of rocks random? Yes. Stated, right? Random sample of 20 rocks. All right, we've done the conditions. Now you've seen it done. It's a pain in the butt. I completely concur with you. But honestly, in a testing environment, you wouldn't have to do it. They're going to say, assume the conditions are met. So if that happens, what you do need to do is make sure you talk about what the test is. And then you would say, like, put it in quotes, assume conditions are met, or problem stated, conditions are met. So don't just leave out the entire plan step. You need to name the test. Okay? All right, moving on. Do step. Do. Okay, so remember the formula for our do step is going to be the sample slope that we found in the table, plus or minus t star times the standard deviation of my slope that I found where? Table. It's all in that table of goodness. So here comes my table. The other one that you can't see, but I can. Here it is. Okay. No. No. All right. We're just going to call College Board and be like, bruh,
You messed up.
you screwed up. I'm sure that somewhere along the way they're going to have proofreaders on the formatting. that'll take it. Okay, so what is the slope?
30.4126.
Right there, isn't it? So 30.4126 plus or minus t star. Do you remember how to do t star? Okay, let's stop and think. T star. We want a 90% interval. So what's in the tails? 0.05. Remember, I'm going to use inverse t with 0.05. And how many degrees of freedom?
2.
Well, n minus 2, right? So 20 minus 2 would give me 18. So tell me what you get when you calculate it. Anybody find it yet? Yep, 1.734. And okay, so where's the standard deviation of my slope in my table? Where is that? Just to the right of my slope. So this is my standard error of my slope. So I pop that in there. And then when I calculate it, I get 26.87 to 33.95. And then we get to conclude. How do we start our conclusions? We are 90% confident that the interval from 26.87 to 33.95 captures the what? True population slope of the LSRL for, and then I'm going to put in my variables. We're going to put in number of balloons and that's my Y, and height. Oh no, not height. I'm sorry, it's weight, isn't it? Okay, how'd that feel? Outside of the conditions, it's not bad, I don't think, is it? No. Outside of the conditions, but alrighty.